Okay, now let me share again. Okay, so let's just recap again really quickly.
Yeah,
We
okay,
have an
so
emulator that is really good.
yeah. Yeah, so as long as your emulator is like a bona fide physical based emulator, that doesn't make the count too round, so to speak, the proverbial cow. Then you're in a position to sample from the distribution, from the theoretical distribution. One, okay, is approximately close to the theoretical distribution, according to your known physical theories. On the other hand, you also have these observations from real data that you can think of as your empirical distribution. Empirical from theoretical differs by thinking of your empirical distribution is basically like a sum of delta distributions. So it's like if you have a data point in your data space, that's represented by let's say a Dirac delta, right? And then you have all the data points, you put them together, that's your empirical distribution. On the other hand, you have the theoretical distribution, which is a sum, let's say, distribution of like how these things actually manifest in nature. Only God knows this theoretical distribution, right? But you, with your wisdom, you came up with these theories and you've managed to approximate that theoretical distribution. So this simulator right here that's animating, you can sample from that ad infinitum, right? And if you say that it's bona fide, then it's like, okay, then use that. Obviously, you must use your actual data as a sanity check to see if um, whatever models you develop out of the simulations make sense. Do reflect the data, do describe the actual data good. But you should definitely, I think this is like a massive role in your project. Um, so why am I putting so much emphasis on the simulator? Because you can control, let's say you define some distribution of configurations. Let's say you have 10 different parameters that control the whole simulation, right? And you specify, okay, this is the distribution of inclinations I expect, of poses, relative poses I expect the star to have. This is the distribution of occultations I expect to have. This is the distribution of star spots that I want to generate in my simulation. And for each star spot, its size, distribution of its size. And it's the also distribution on the differential rotation for each star. You define these priors, right, on your parameters, and then you press start. And then, you can have like another episode of simulations with different priors. What I guess really what the trick here is to choose a good prior on each of these parameters. Like this is where really the domain knowledge comes into hand. Now, okay, let's assume that the choice of priors is, I dare say, not such a big problem. Let's say that it's solved, right? You press start, you generate your data, and then you fit your models. Those are going to be models that basically they have to identify what those generating parameters were. It's like an inverse problem, right? This is where Bayesian inference, this is what Bayesian inference is about. Is like you assuming that you use a certain generative model. By generative, I don't mean things like GANs. I mean probabilistic model, right?
Mm-hmm.
A generative distribution of data. You want to see the data that come out of a simulator. Now use that data to do inference on your probabilistic model. And then the posteriors that come out, if they match the parameters that you used for your generation, that's basically like a probabilistic sanity check. Does that make sense, or should I clarify that a bit? Let's say, okay, let's say something more concrete. Let's just play with one parameter, right? Let's say that all things being equal, you're only deciding to play with differential rotation, how fast the star is spinning. Maybe that's not the same as differential rotation. Maybe it's
yes.
Maybe, okay, let's something simpler. Let's say the number of star spots. Right? Let's say that's just one parameter you're playing with, and you have a distribution there that it looks like a Poisson, right? You decide a Poisson distribution on the number of star spots, and the Poisson kind of looks like, from the way you see it, like, kind of like that. So based on that Poisson and its particular parameters, you press start, you generate your data, your simulations, and then now from that, you're trying to go backwards. Like, you're trying to infer, based on the data, what are the parameters of that Poisson distribution. Making sense? Now, because now I'm thinking concretely in terms of that prior, because before it sounded a little bit vague.
But how do you do this mechanically? I mean, and the cost. One of the things that I heard from, I mean, that came up in some of the things that people raised as obstacles is the cost. So people were talking about Markov chain, MCM, Monte Carlo, to explore this parameter space. And and people have done this in the past, and so you say, okay, I'm going to try to kind of like use only two spots. But if you do 3 spots, 4 spots, each one of them you have to specify latitude, longitude, and area, let's say. So then it becomes the volume that you're trying to sample with a technique like this is just so vast that it becomes impossible to do. So do you have an idea of a better technique to do this kind of exploration and to try to underpin this?
The whole area of research that you touched on. So you mentioned the buzzword MCMC. That's like, basically it's like stochastic sampling, stochastic inference, right? So inference is about determining probabilistically certain parameters of a generative model, like, for instance, the number of the distribution of the star spots, the number of star spots, inferring that distribution from data, right? That's inference. Now you can do inference exactly, which means that you have a way to exactly, like, analytically infer, just by sheer mathematics, just by doing algebra, to get the posteriors. That does happens in exceptional cases, like, for instance, when you have Gaussian data, like you said, you observe some variables and then you're trying to infer what the posterior is. That's just like falls out by linear algebra, just analytically. That happens almost never in the real world, because sometimes it happens that your parameters are kind of weird combination of, let's say, okay, one is Poisson, might be a gamma. It's kind of like this weird zoo of distributions that don't really play well together. But there's still a mathematically valid posterior the other way. It's just that you can't reach that analytically. So this is when people now try to think proximally. How can we approximate the posterior? We either get it by doing deterministic inference or stochastic inference. Deterministic inference is basically all your variational methods. Variational Bayes is what it's called. And it's called deterministically because basically you're trying to approximate posterior by solving an optimization problem. I'm not going to...
Right. So that's what MCM will be?
I'm not going to get into this right now, but all I'm saying is that there are ways to approximate a posterior by solving an optimization problem, and there's tons of libraries for this, and it's called variational base. This is like a whole family of methods. It's kind of related to variational encoders, but it's like yeah. Anyway, let's not get into that. Now, MCMC is about stochastic inference, and that is a kind of an irony, because you're trying to solve a Bayesian problem by relying on frequentist methods. Basically, you're saying, why don't I sample from this generative model that I have, that I'm kind of like surmising that is true to the theoretical distribution, and you're generating it with certain configuration, the certain parameters. So you're just like saying, okay, let's choose parameter, generate data point, and then you have a rule at the end. You say the rule kind of gives you the likelihood of that data point matching your data. Or in other ways, it's like it is the likelihood of the data given the particular parameter setting of the generative model. So the likelihood function tells you like what is it's like kind of a score to say what is the likelihood that this data was generated by these parameters. So now it's kind of like this stochastic exploration. So by having this likelihood function, I think it stopped. I'm sure.
Yeah, because I think you saw now the curves. So I think now that I'm recording, I think it's nice to see you talk.
Yeah, so basically it's like kind of this game where it's like, okay, proposal parameter, see what the likelihood of the data given the parameter. And then you have a rule that says, okay, depending on the score, I'm going to move this way or that way to the parameter space.
Mm-hmm.
And then what you can do, the most naive thing is like you can explore completely randomly the parameter space, and then you get your likelihood at the end. And that will kind of like say basically like this is what in the end you get like a posterior, you can give you a posterior of the parameters, right? But this is very naive, and it's probably like never going to converge because obviously the dimensions explode, and it's really hard to search in that space. So you have to make some assumptions. And there are there's a whole universe of methods about how to properly explore the parameter space. That in the end, what you don't really get a posterior in the way of the it's not like you get a curve or something like that. You get samples from the parameter space, from the posterior of the parameter space. So basically, like depending on the likelihood, how the likelihood function basically gives you a score with respect to each parameter setting. All these things kind of like sum together and it gives you a weighted average of your parameters. Now, then what's nice about stochastic methods is assuming that you have infinite time, eventually you will converge to the true posterior, right? So the question is like, how long are you willing to wait? And there's like a joke in sampling theorists where they're saying the fastest algorithm is just wait until the next method is invented. And then use that.
So how would you do it?
And that's kind of true, right?
Like if you have to pick,
right.
If you have like a limited amount of time and you want to approximate this, which technique would you recommend? Out of all these zoo in your
well, I would definitely go with Gaussian processes as a definitely that's because that's really good way to characterize distribution over function spaces, right? So if you think of the Lie curve as a function, because it is a function, it's a function of determined by these parameters that we just hypothesize. You can say, well, okay, my generative model is one that I have a Gaussian process that is defined by these star parameters, and then it's kind of like you see hierarchy, right? So you've got star parameters, you have some parameters over that. These generate the parameters, and then the parameters define your GP, your Gaussian process, and then the GP basically like generates for you functions over time, but they have this kind of they have the intrinsic noise in them. So basically they will give you any kind of curve that matches your data up to the noise. Yeah. So then the game is based on the data. Can you do backwards inference? Can you backpropagate the uncertainty to take into account the observation noise that you have in your curves, but also the uncertainty that you have in your priors of your, let's just call them hyperparameters, basically.
Yeah.
Yeah. So there's going to be some interplay between approximate inference and yeah, but I'm not really, I don't want to say, okay, this is the sampler that you want to use. There are probabilistic programming packages out there that can do this for you, and I think from what I've seen so far with the data, it's not the size of the data is not that big, at least because you want to do this on like you can do this on individual on an individual curve basis, which is like basically you've got one distribution, one posterior distribution of parameters per star, right?
Mm-hmm.
But then you have also something else which says something more general about these stars in general, like what distribution do you expect these stars to have in aggregate? What is this theoretical distribution that we're talking about, right?
Yes, exactly.
And the thing is that this is all the stars are dependent. They're a dependent random variable because they all follow this thing. They all come from the same theoretical distribution. Like stars adhere to some physical laws, right? So if you make any statements about one given star, let's say that for some reason you've managed to pinpoint exactly its parameters, that automatically reduces your uncertainty about other stars, because you found out something about that one star, about our own star, that tells you automatically something about all the other stars in the universe.
Yes.
Right? So that's, in that sense, the stars are dependent random variables.
Yes. And I mean, there may be stars that are very different from each other, but there are certainly stars that are very similar to each other. And so, so one of the things that I hear from you is that it also will help us narrow our posterior distributions if we take advantage of the fact that these stars are not objects in a complete vacuum, but they're physical objects with similar properties. And that stars of similar sizes, for example, or similar temperatures, or similar class, or whatever.
That's a much better inference problem, right? You can think of it as the grand Bayesian model of stars as in the context of this problem challenge. But
and once you narrow this, can you build on that to now address each individual star, for example? Like you work on groups, and then you say, okay, as a family, as a group, as a population, these stars have this distribution.
You can start by You can start by doing inference on each, let's call it mini model, because the individual star model. Once you, let's say you kind of converge to some posterior for each star, for each curve that you have, then you can start exchanging information between the different models and then kind of fine tune their posteriors. But to that, I think I would always start by doing inference on individual curves first. And yeah, so the simulator that you have though is really interesting because it allows you to play a very different game. You know, you can like say now you don't need to rely on on a on a mathematical model. Well, no, let me just rephrase that. On a on a generative model, on a probabilistic generative model to generate data like you would do in an MCMC, where you're basically saying I'm generating data from some posterior. What you you could just use a simulator to generate data.
So I wanted to ask you if I, and this is not something you need to answer right now, but if you think about a similar application like this one that you have come across in other contexts, something that we could learn from someone that is trying to turn time series into something, or even images into something. It's fine. I mean, but kind of like that follows this process that you're suggesting, that you're talking about, where we have like these distributions, a generative model and real data and observations that are bounded by physical or common parameters, so they are not completely independent from each other. And how people tackle this, how they arrange their data, how did they follow like through this, we can learn from that.
I'm blanking right now.
Don't worry.
So I mean, okay, maybe like one thing that I find some parallels with our problem actually, because we have low resolution images from rivers, right? And what we're interested in is detecting, mapping the rivers, like basically seeing where water flows. And water has a certain spectral signature that becomes aliased when you downsample the image too much, as you're probably aware. You're familiar now with downsampling quite a lot. The question is, when you can actually see it, you as a human at least, is beyond recognition in water. There's still signal. There's still signal there. There's like because you've got all these multiband and water is the hint of water is still there, right? It's not like because you can't see it doesn't mean it's not there. That is especially true when you have a time series of that, a time series of low res spectral signature, and the temporal aspect of it is key. And that's the analogy I see with your problem, is because if you just get, I mean, of course it's going to sound dumb, but if you just get one time point, you can't make statements about a temporal phenomenon. But flowing water also is a temporal phenomenon. You need time series of it to make statements, right? So there's information in the object in time. So I'm also thinking how can we use things from the stellar transit literature that we could potentially use, because you've got these subpixel motion that might be somewhere in there in like the spectral mixed signal that we might be able to tease out when we look at it in time. And this is definitely something in remote sensing have looked at, like basically do spectral unmixing from a time series of images. So spectral unmixing is the keyword here.
Yeah. Well, we will, if we find anything, we'll definitely share it with you guys.
Yeah.
Yeah.
Yeah, we were actually thinking of interviewing Brett. I don't know if you would have the time, but you know, we're very open-minded. Maybe there's a connection here that no one has thought of.
Yeah, I think
It's
that's
very
basically.
difficult because yours is a univariate time series, ours is a time series of images, but yeah, it sounds like a hard problem. I mean, is in the sense that it's just it's hard to tease out that signature from many images.
Yeah.
Um,
Okay.
um,
Awesome. I
it would
think.
be really interesting, like maybe just as a starter, what I would do is that try to play with that simulator and see what, you plug in a prior, see the data that comes out. It's just about like just maybe seeing by eye, see what the real data looks like, what the simulated data looks like, and that will give your team an intuition about what are reasonable priors for this data. Because it's like, I mean, I'm sure no one has any. I'm sure people have like clues about what the prior should be, but the thing is, have people actually played with all different kinds of configurations? So you need to create like your own star spot sandbox.
Yeah. I mean, I think my understanding from talking with the other experts, the astro experts, is that our prior, ultimate prior, and first and foremost, that we always think about is the sun, right? The sun, because we have it so well observed. And so it's not unreasonable to use that prior, but it's not necessarily. I mean, there is no reason why all stars, especially in the catalog that is as that samples so many different kinds of stars as the ones that we're working with, will just be like the sun. And then when it comes to trying to come with reasonable samples, reasonable priors that are model informed, the complexity of the model so far has been more than what any researcher has been able to grasp. So as soon as you add one more spot, it just is too much, right? And then you don't know, and then it just becomes. And so, but I mean, I could be wrong, but that's my perception of the thing. That in this moment, the best prior we have is the sun, and any other prior that we have is just very, very basic and not very well defined. So that's one of the things that when I talked with you last time resonated with me, is that can we make priors that are more, not necessarily based on the sun, but based on the data on these distributions that we have in some way. And what you're saying about, yeah, like taking these groups of stars and using that to define these spaces that we could potentially use as priors for other stars. And
Yeah, kind of
like
yeah, it's like what you know about certain stars can inform the inference about other stars and vice versa. Because ultimately you want to create a global distribution that says things about all stars.
yes,
Not
but
just about one.
all stars and also individual stars.
Yeah. Right,
Both.
right. Yeah.
Yeah.
Yeah. Yeah. So that's how I see the big picture, like the exact mechanics, how you're gonna inference from that. I don't know, but I think your team is very well equipped to figure that out.
Thank you. And
Exactly what inference engine you're going to use, whether it's going to be stochastic or variational. Maybe you can even get away by doing exact inference on some of these priors, because you know, so, some cases certain priors are conjugate. You know, you can say I have a certain prior distribution on one parameter, and then there's like another hyperparameter in that, and the hyperparameter is controlled by another distribution. But sometimes you can do exact inference on these hyperparameters because they're conjugate, is what we say.
And let me ask you a quick question. And this is now a personal curiosity. We have hundreds, potentially hundreds of thousands of these curves.
Yeah.
And let's say, and a ballpark it. Let's say we have 50,000 curves that we can somehow say, from 10,000 to 50,000 curves that we know, we can say this has star-spurs crossings. One of the things that I'm curious is, can we cluster these curves in some way to find families of stars based on the light
Totally.
curves?
Yeah. Of course. There's
And
yeah, because now you're talking about um, I think this falls really nicely into the whole generative model of the global generative model, right? If you hypothesize that the parameters of stars, if you think of the parameter space, and each point is like the parameters that define the way the star sends you the light. I think it's very interesting to see that forms clusters, and then what you want is find the parameters of the clusters.
yes.
So yeah, like so now the cluster has parameters that you want to infer, and it just kind of like builds up. It's not just about finding the distribution of individual parameters of the star, but also you want to find the parameters of the clusters of the parameters. Yeah, it just adds more levels to the hierarchical Bayesian model. Maybe this is something that you can do in a multi-stage approach, where you say, once let's say that, for every star, you say this is a point estimate on the parameters. Let's say you simplify the problem, right? Let's say you compute a point estimate. What's you found the posterior on the parameters of a star, and you find the mode, like say the configuration that is the maximum probability, posterior probability, and you take that as your point estimate, and you do this for every star. So now you have a data set of star parameters. Now you can do clustering in that. You can do whatever clustering you want. You can do Bayesian clustering. You can do deep learning clustering, whatever. You can like create you can do a TSNE like the GNSS team did last year, which is not probabilistic, but basically give you a point estimate on the clusters. And what that is like it basically finds some kind of, it gives you a 2D projection of those clusters. Yes. But it's a projection on some kind of very non-linear manifold in this parameter space of the clusters. Yeah.
But do you do the estimation of the point estimate for each star first, or do you cluster the light curves? Because the light curves of the different stars will have the similarities already.
Yeah.
Even if you don't know anything about the star,
It's kind of one and the same, right? Like, what does it mean to say you're putting two Clyde curves in the same cluster? What does that mean? If you think about that, you can translate that to saying, well, if they're in the same cluster, that means that these curves have certain parameters that are really similar, right? So it's like equivalent to say one or the other.
But we'll do one, like if we work on curves, I guess what I'm trying to say is, if we work on the curves, will that help us define better priors? Because we're not necessarily, if we know these curves are similar.
So yeah, what I just described was kind of like a simplified stage-wise approach to finding clusters, which is like, you're done with the estimate with the start parameters, now you're finding clusters. Or you can do this end-to-end, back and forth, where you're doing some inference on the individual stars.
Yes, I see what you mean.
And then you're doing inference on the cluster parameters, and then you're doing, based on that, you're doing inference on the individual stars, because like one informs the other. And actually, that might be a good way to make to inform the star models, but also the individual star models, but also the global star, if that makes sense.
Yeah, it does make sense. Yeah. I'm taking notes as we speak.
Yeah. I think that's it.
Awesome. Thank you so much for your time, and I'll let you know as we go.
Cool.
And yes, there may be things that we find that they are useful for your team as well.
Yeah, we touched on a lot of things, but for tomorrow, I think I'm gonna watch the videos you sent me, and maybe I have a better idea of